Imagine waking up tomorrow and your phone is dead. Not low battery, brick dead. You flip a light switch, nothing. The fridge, the Wi-Fi, the microwave, all dark. You walk outside and your neighbor is standing in their driveway staring at their car like it just insulted them. The streetlights are out. The gas station down the road has a handwritten "closed" sign taped to the pump. Now multiply that by an entire continent. For months. That is not a Netflix pitch. That is the actual projected outcome of a severe solar storm slamming into Earth's magnetic field at full force. Power grid transformers that weigh hundreds of tons and take over a year to manufacture, melting from the inside out. Every GPS satellite in orbit scrambled. Planes grounded. Hospitals going dark. Internet backbone cables on the ocean floor flooding with rogue electrical currents. Lloyd's of London estimated the damage to the United States alone at up to $2.6 trillion. Recovery time? Scientists in China calculated 4 to 10 years. You might be thinking, that sounds extreme. So consider what happened in May of 2024 when a solar storm hit Earth and knocked GPS signals across the American Midwest off by up to 230 feet. Farmers in the middle of planting season watched their GPS-guided tractors veer off rows and plow through already planted fields. They described their machines as demon-possessed. Total damage to U.S. agriculture? Over $500 million. And that storm was rated a G5, the highest on the scale, the strongest in 20 years. Produced gorgeous auroras as far south as Mexico and Spain. It was also a gentle tap on the shoulder compared to what the sun is truly capable of. We know this because it happened before, and the only reason it didn't end the modern world is that in 1859, the modern world didn't exist yet. On September 1st, 1859, an English astronomer named Richard Carrington was sketching sunspots from his private observatory in Surrey when something impossible happened. A sudden white light flash erupted from one of the sunspot groups he was drawing. It was the first time in history anyone had directly witnessed a solar flare with their own eyes. What Carrington couldn't see was the invisible weapon that flare had just fired at Earth. A coronal mass ejection, a cloud of magnetized plasma with the energy equivalent of 10 billion atomic bombs, was screaming toward the planet at a speed that would cover 150 million kilometers in just 17.5 hours. Typical coronal mass ejections take several days to cross that distance. This one arrived before the next sunrise. When it hit, the effects were immediate and global. Telegraph systems across North America and Europe failed simultaneously. Operators reported sparks showering from their equipment in violent bursts. Some telegraph stations caught fire as the induced currents overwhelmed the wiring. Papers ignited on desks. In several documented cases, operators received electric shocks strong enough to knock them backward from their stations. The damage stretched from London to Boston to Melbourne. The auroras that followed were unlike anything anyone alive had ever seen, and they lasted for days. People in New England could read the newspaper at midnight by the glow in the sky without lighting a candle. Gold miners in the Rocky Mountains woke up and started making breakfast at 2 in the morning, absolutely convinced the sun had already risen. Sailors in the Caribbean reported the sky glowing red and green overhead. The northern lights were visible as far south as Cuba, Jamaica, El Salvador, Hawaii, and Colombia, nearly touching the equator. And then came the strangest detail of all. 2 telegraph operators on the line between Boston and Portland, Maine, disconnected their batteries entirely and continued sending messages back and forth using nothing but the electrical current generated by the storm itself. The sun was literally powering their communication lines. This event became known as the Carrington Event, and it remains the most intense geomagnetic storm in recorded history. Ice core samples later confirmed it was twice as powerful as any solar storm in the previous 500 years. Now, in 1859, the world ran on horses and telegraphs. The damage was dramatic, but survivable. Telegraph wires could be repaired in days. Nobody depended on GPS to land an airplane or guide an ambulance through traffic. There were no satellites to fry, no internet cables to overload, no banking systems running on servers that need uninterrupted power. Today, every one of those systems exists, and every one of them is vulnerable. There are roughly 10,000 active satellites circling the planet right now. SpaceX alone has launched over 6,000 Starlink internet satellites. The global economy moves trillions of dollars through electronic systems every single day. Modern agriculture, as the May 2024 storm proved, cannot function without centimeter-accurate GPS. Even the water that comes out of your tap relies on electric pumps managed by automated systems. A Carrington-class event would not just break things, it would break the systems we use to fix things. You cannot order replacement transformers when the internet is down, the phones are dead, and the factory that builds them lost power too. The probability of a Carrington-class storm hitting Earth within any given decade is estimated between 1 and 10%. Those are not comfortable odds for an event that could set modern civilization back by a decade. And we already know this is not a theoretical risk, because we came terrifyingly close to finding out firsthand. On July 23, 2012, the Sun launched a coronal mass ejection that was, by every measure, on par with the Carrington event. Two nearly simultaneous eruptions combined to blast magnetized plasma into space at more than 2,000 kilometers per second. That is 4 times faster than a typical solar storm. The energy released was equivalent to 1 billion hydrogen bombs. The reason it traveled so fast was almost poetic in its cruelty. A smaller coronal mass ejection 4 days earlier had swept the path between the Sun and Earth clean of solar wind plasma. The highway was empty, so when the big one launched, there was nothing to slow it down. The storm ripped through Earth's orbital path at 3,300 kilometers per second and slammed into the Stereo A spacecraft, a NASA solar observatory that happened to be sitting in exactly the right spot to record the whole thing. Because Stereo A was far from Earth and not connected to planetary infrastructure, it survived the encounter and beamed back data that confirmed what scientists had feared. This was a Carrington-class superstorm. The southward-oriented magnetic field it carried was precisely the orientation that drives the most violent magnetic reconnection when it collides with Earth's northward field. Earth was not in that spot. The planet was on the other side of the Sun at the time, having rotated past the blast zone just 9 days earlier. 9 days of orbital rotation. That is how close the modern world came to a multi-trillion-dollar infrastructure collapse, widespread satellite destruction, and potentially years without reliable electricity in the summer of 2012. Daniel Baker, a space weather researcher at the University of Colorado, later said that if the eruption had occurred just 1 week earlier, we would still be picking up the pieces. Almost nobody heard about it. For most of recorded history, humanity's strategy for dealing with solar storms has been the same strategy a deer uses when headlights appear on a dark road. Stare at it and hope for the best. We built better forecasting systems. We developed early warning satellites. We hardened some critical infrastructure. After the March 1989 geomagnetic storm knocked out the Hydro-Quebec power grid, the response was dramatic, but only after the fact. That storm hit on March 13th. Within 90 seconds, voltage fluctuations triggered 15 simultaneous failures across the Quebec transmission network. The entire provincial grid collapsed like dominoes. 6 million people across the province woke up to no electricity, no heat, and no answers. Schools closed. Businesses shut down. The Montreal Metro stopped running. Hospitals switched to backup generators that were only designed to last hours, not the 9-hour blackout that followed. And that 1989 storm was not even close to Carrington class. It was significantly weaker. Yet it still brought one of the largest cities in North America to a standstill in under 2 minutes. The Canadian government responded by spending roughly $1.2 billion upgrading the Hydro-Quebec system with better grounding and transformer protections. The United States introduced federal reliability standards for geomagnetic disturbances. Progress, absolutely, but still fundamentally reactive. Predict the storm. Brace for impact. Pick up the pieces afterward. Nobody had seriously proposed actually stopping a solar storm before it could do damage. The sun is massive. Space is enormous. The forces involved are measured in billions of hydrogen bombs. The idea of intercepting that kind of energy seemed like science fiction, until a physicist at Boston University asked one simple question: what if nature already showed us how to do it? Brian Walsh is an associate professor of mechanical engineering at Boston University's College of Engineering. He runs the Space Physics and Technology Lab, and for years he has studied one specific thing: the boundary where Earth's magnetic field meets the solar wind. That boundary is called the magnetopause, and it is the front line in an invisible war that has been going on for billions of years between Earth's magnetic field and the sun's constant barrage of charged particles. Understanding how the magnetopause behaves during solar storms is the key to everything that comes next. In January 2025, Walsh launched a telescope to the moon. The instrument, called LEXI, short for Lunar Environment Heliospheric X-ray Imager, rode aboard Firefly Aerospace's Blue Ghost lander on a SpaceX Falcon 9 rocket from the Kennedy Space Center in Florida. The 24-pound instrument had been sitting in a display case at NASA's Goddard Space Flight Center for a decade before Walsh pulled it out, refurbished it, and convinced NASA to fly it to the lunar surface. From the moon, LEXI captured something nobody had ever seen before: global X-ray images of the magnetopause, the exact boundary where the solar wind crashes into Earth's magnetic field. Previous missions had only observed patchy segments. LEXI gave Walsh the complete picture. And what that picture showed was a natural phenomenon that changed his approach to the problem. Material from Earth's upper atmosphere naturally peels off and drifts outward toward the magnetopause. When it gets there, it reinforces the boundary. Earth was already protecting itself, in a small way, by sending its own atmosphere out to thicken its magnetic shield. Walsh had been studying this boundary for over a decade. His work at the Boston University Space Physics and Technology Lab focused on understanding exactly how and when the magnetopause opens and closes under solar pressure. The LEXI data from the lunar surface gave him something no researcher had ever had before: a full, global, real-time view of the process in action. And what he saw triggered an idea that nobody in his field had ever seriously proposed. What if you could turn that natural reinforcement process up? What if you could increase the intensity of it artificially, flooding the magnetopause with far more plasma than Earth's atmosphere produces on its own, and give the planet a much stronger version of the shield it already builds for itself? Walsh started running the numbers. The idea became a simulation. The simulation became a paper, and the paper became StormWall. Before explaining how StormWall works, you need to understand why solar storms are so dangerous in the first place. And the answer comes down to one word: reconnection. Earth's magnetosphere is an invisible bubble of magnetic energy surrounding the planet, generated by the churning molten iron in Earth's core. Under normal conditions, this bubble deflects the constant stream of charged particles the sun throws at us. Think of it like a force field in a science fiction movie, except it is real and you would not be alive without it. The problem is that the sun's magnetic field and Earth's magnetic field can sometimes line up in a specific and dangerous way. When a coronal mass ejection arrives carrying a magnetic field oriented southward, that field can merge violently with Earth's northward pointing field lines at the magnetopause. Scientists call this process magnetic reconnection, and it is exactly as destructive as it sounds. Imagine two magnets with opposing poles being forced together until the field lines snap, reconfigure, and release stored energy in a violent burst. That is reconnection, except it happens across an area the size of a continent at the edge of space. Reconnection essentially punches a hole in Earth's magnetic shield. It opens a channel through which massive amounts of energy from the solar storm pour directly into near-Earth space. That energy floods into the magnetosphere, races along magnetic field lines toward the north and south poles, dumps into the upper atmosphere, and triggers everything from stunning aurora displays over Norway and Canada to electrical grid failures in Quebec and cascading satellite malfunctions in orbit. The stronger the storm, the bigger the holes. The bigger the holes, the more energy gets through. A Carrington-class event would open channels so wide that the magnetosphere would compress inward to roughly half its normal size, leaving satellites and space stations completely exposed to the raw solar wind. StormWall targets this exact process. If you can disrupt magnetic reconnection at the magnetopause, you can dramatically reduce the amount of energy that gets through to Earth during a storm. On June 2, 2026, Walsh and his colleagues at the University of Michigan published their proposal in the journal Space Weather. It was the first peer-reviewed study in history to propose actively deflecting solar storms instead of predicting them. The system is elegant in concept. 6 spacecraft would be launched into geosynchronous orbit about 36,000 kilometers above Earth's surface. That altitude matches the planet's own rotation, so the spacecraft would hover in fixed positions relative to the ground below. Each spacecraft would carry giant canisters loaded with an alkaline chemical element. The leading candidates are barium, lithium, sodium, or calcium. Even salt water could potentially work. When space weather forecasters detect an incoming coronal mass ejection, which current monitoring systems using spacecraft like the Advanced Composition Explorer at the L1 Lagrange point can do with roughly 15 to 45 minutes of warning, an operator on Earth would send the command to release the material. The canisters would open, venting the chemicals into the vacuum of space. Once exposed to sunlight, the chemicals would undergo a process called photoionization. Ultraviolet radiation from the sun strips electrons from the atoms, transforming the gas cloud into electrically charged plasma almost immediately. This freshly created plasma cloud would drift outward along natural electromagnetic pathways toward the magnetopause. Once there, it would reinforce the boundary, adding mass and density to the region where reconnection occurs. The extra plasma makes it significantly harder for the solar storm's magnetic field to merge with Earth's field. The reconnection process is disrupted. Energy that would have poured through gets deflected around the planet instead. From canister release to full magnetopause reinforcement, the process would happen within minutes. And critically, the artificial plasma would follow the same electromagnetic pathways that natural atmospheric material uses when it drifts to the magnetopause on its own. Walsh was not inventing a new physical process. He was amplifying one that Earth already performs, at a scale that could make a real difference during a major storm. Co-author Daniel Welling, a space physicist at the University of Michigan, described it in the simplest terms possible. He said it was as if you could install an airbag in the magnetosphere. Walsh and his team ran extensive computer simulations of the system using models of real geomagnetic storms. The results showed that StormWall could reduce the intensity of a major solar storm by more than 50%. Both key measures of geomagnetic storm severity, the auroral electrojet index and the cross-polar cap potential, dropped dramatically in the simulations when the artificial plasma cloud was present. 50% might not sound like total protection, but for context, that is the difference between a storm that destroys power grid transformers across a continent and one that causes temporary disruptions utility companies can manage in real time. If you're still watching at this point, you're clearly someone who appreciates the kind of science that actually matters. Consider subscribing. This channel covers space, physics, and the engineering ideas that could change the future. Every week. No fluff. Now the obvious question. How much stuff are we actually talking about launching into orbit? The paper lays it out with uncomfortable specificity. The total required payload mass across all 6 spacecraft would be approximately 436,253 kilograms. Walsh described this as roughly equivalent to a dozen oil tankers worth of material. That is an enormous amount of mass to get into geosynchronous orbit. The researchers acknowledged that this is the single biggest obstacle to making StormWall real. Getting hundreds of tons of chemical payload to an altitude of 36,000 kilometers is not cheap, and it is not easy. What changes the equation is the new generation of heavy lift rockets. The paper specifically mentions SpaceX's Starship and China's Long March 9 as launch vehicles capable of delivering the required payload. Starship can carry 100 to 150 tons to low Earth orbit in its reusable configuration, and roughly 27 tons to geostationary transfer orbit. SpaceX has priced dedicated Starship launches at approximately $90 million each. Walsh pointed out something that reframes the cost discussion. Power grid damage from a single Carrington-class event would top $2.4 trillion. Private companies are now investing billions in space infrastructure. Some are even planning to build data centers in orbit. As the value of assets in space increases, the math on protecting those assets starts to look different. And there is another factor nobody talks about enough. StormWall would protect every nation on Earth simultaneously. You could not build it in a way that helped only one country. The magnetosphere wraps around the planet. A shield that reinforces the magnetosphere shields everyone. Walsh put it plainly when he said that if you built it, if it was deployed, it would help all people on the planet. StormWall also answers one of the biggest concerns people raise about any large-scale intervention in Earth's environment. What about the mess you leave behind? Geoengineering proposals for climate change, like injecting sulfur aerosols into the stratosphere, generate fierce opposition, partly because those particles linger for months or years and affect weather patterns worldwide. StormWall does not have that problem. The plasma cloud it creates dissipates naturally within about 6 hours. The magnetosphere flushes the material out on its own along natural electromagnetic pathways. Nothing accumulates, nothing builds up, nothing drifts back down to Earth. Walsh has been clear about this distinction. Unlike geoengineering proposals that would alter the atmosphere for extended periods, StormWall's effects are temporary, targeted, and self-cleaning. The Science Journal article by the American Association for the Advancement of Science coined a new term for this kind of work. They called it helioengineering, a deliberate intervention in the near-Earth space environment, but one that leaves no lasting footprint. That clean exit is also the system's biggest limitation. StormWall, in its current design, is one and done. Once the canisters are emptied and the payload is photoionized, the spacecraft are inert. They cannot be refilled. They cannot fire again. If a second storm arrives the following week, you would need a fresh set of spacecraft loaded with fresh material and launched to orbit. That expendable nature is the trade-off. You get a system with no long-term environmental consequences, but you also get a system that works exactly once and then needs to be completely replaced. Walsh's team is already working on potential solutions. Their next research priorities include finding ways to have the material required, simulating pulsed releases that could extend the system's active window, and exploring more efficient orbital positions. They also want to test different chemical compounds to find the most effective elements for disrupting reconnection. So where does StormWall go from here? The June 2026 paper is a feasibility study, not a construction blueprint. Walsh and his colleagues have demonstrated that the physics works and that the required launch capabilities exist. That second point matters enormously. This is not a proposal that requires technology we haven't invented yet. Heavy lift rockets, capable of delivering the payload, are already flying. The chemical compounds are well understood. The orbital mechanics are standard. The space weather forecasting systems that would trigger the release are already operational. What remains is funding, political will, and additional engineering work to optimize the system. Walsh has said he is confident the team can bring costs down further. The research agenda includes studying whether a smaller payload deployed at more efficient orbital positions could achieve the same protective effect. There is also the question of international cooperation. Because StormWall protects the planet by default, it could become one of those rare engineering projects that every nation has an incentive to support. No country benefits from having its neighbor's power grid survive while its own goes dark, because a Carrington-class event would not stop at national borders. The cascading failures would be global. Walsh, speaking from his lab at Boston University, summed up the shift in thinking that his research represents when he said that people have always thought space is huge, the sun is massive, and we have to sit there and take whatever it gives us. What his team found is that we can actually impact it. The physics of interference at the magnetopause boundary works at scales that humans can achieve with existing rocket technology. For 167 years, since Richard Carrington first watched a solar flare erupt from his observatory in Surrey, humanity's relationship with space weather has been purely reactive. We watch, we measure, we warn. And when the storm hits, we endure the damage and rebuild. StormWall is the first serious, peer-reviewed proposal to change that relationship, to stop treating solar storms as inevitable acts of cosmic violence and start treating them as an engineering problem with an engineering solution. Whether it gets built in the next decade or the next century depends on a question that has nothing to do with physics. It depends on whether governments, space agencies, and private companies decide to invest in planetary protection before the next Carrington-class storm forces our hand. Consider the timeline. The Carrington Event happened in 1859. A comparable storm narrowly missed Earth in 2012. The May 2024 Gannon storm caused $500 million in agricultural damage alone, and it was not even close to the worst the Sun can produce. Scientists estimate that Carrington-class events occur roughly once every 100 to 250 years. We are 167 years past the last one. The probability of another hitting Earth within the next decade sits between 1 and 10%. Those are the odds we are playing with. Every year without a shield, we roll the dice again. And the stakes keep climbing as we put more satellites into orbit, more data centers online, more infrastructure under the control of systems that cannot survive a direct hit from the Sun.